Today we're going to talk about sample space and number of outcomes. Sometimes it is useful to know the number of outcomes in a sample space without generating the sample space. So instead of coming up with all the possible outcomes, maybe it's nice to just know how many possible outcomes there are, especially when we're talking about probability. All right, so the counting principle. Basically, this is a shortcut to find the total number of outcomes in a sample space. You can use this when order matters and the repetition is allowed. Okay, so you could repeat the same choice over and over again and use this counting principle here. Basically, you count up the number of ways to do each stage of it, and you multiply those number of ways, and that'll give you the total number of possible outcomes. So I want to create a blank for each selection, write the number of outcomes for each selection on the blank, and then multiply the blanks. All right. Now, when we get into some more difficult examples, we're going to have like special conditions on some of those blanks. You got to do the special condition ones first. But to start here, we got some basic ones. Deli has 5 types of meat, 2 types of cheese, and 3 types of bread. How many different sandwiches consisting of? Okay, so I want 1 type of meat. So my first blank here, that's going to be for meat. All right, and I want 1 type of cheese. So that blank there is going to be for how many choices I have for cheese. And then 1 type of bread, right? So meat, cheese, and bread. All right, well, how many choices do I have for meats? 5. 2 choices for cheese, and 3 types of bread. All right, 3 times 2 times 5 is going to give you a grand total of 30 different kinds of sandwiches. All right, Paloma has 3 jackets, 6 scarves, and 4 hats. Different number of outfits consisting of a jacket, a scarf, and a hat. So I need 3 blanks, jacket, scarf, and hat. So 3 jackets, 6 scarves, 4 hats gives me 72 total outfits for that. You can see these are really kind of basic ones, right? Just refreshing your understanding of counting principle here. This one's a little bit different. John is going to line up his 4 golf trophies on a shelf in his bedroom. So how many things is he going to line up? 4. How many different possible arrangements can he make? So let's see. We got this first, second, third, and fourth. So how many choices do I have for this first spot on the shelf here? There's 4 trophies, so I have 4 choices. Once I put one up there, now I have 3 choices. Now I have 2 choices, and then there's only 1 for the last one. All right, that is also called 4 factorial. Remember that? Okay, 4 times 3 times 2 times 1 is 4 factorial, which is equal to 24. All right, how many 3-digit numbers are possible using the digits 1 through 9? Okay, now this says using the digits 1 through 9. So like for an example, a 3-digit number like 575, okay, how many numbers are there like that, right? That's just an example of a 3-digit number, right? So how many choices do I have for that first digit if I have 1 through 9? Well, I have 9 choices. And in fact, for the next one, it could be the same digit or something different. It could be any one of 1 through 9 choices. So 9 choices for all of these. So that is 9 times 9 times 9, which is 9 to the 3rd. Okay, I don't know what that is off the top of my head. 81 times 9 is 729. 729. Okay. 729. Okay. How many 3-digit numbers are possible using the digits 0 to 9? Now here we have a little bit of a problem here. All right, with that first spot there, like if I have like something like 036, that's actually a 2-digit number, right? So I have like a special condition on this first thing. This first thing cannot be 0. So I have actually for choices 1 through 9, which is 9 choices. But after that, I could have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have 10 choices for the subsequent digits. So it's 9 times 10 times 10, which is 900, right? How many 3-digit odd numbers are possible using the digits 0 to 9? So what I have here is it's got to be an odd number. And that's only going to be odd if the last digit is odd. So that one has to be odd. That's a special case. And again, since I have 0 to 9 here, this one can't be. I'm going to change this question. Let's change this to 1 through 9, okay? Let's change that to 1 through 9, rather than having that 2 special conditions, all right? But what I want to handle is this special condition first. How many digits are odd in 1 through 9? 5 of them, right? And then how many choices do I have for the first digit? Well, 1 through 9 and 1 through 9, right? So 9 times 9 times 5. 9 times 9 times 5, 81 times 5. Let's see, 405, 405. So remember I changed that question 1 through 9, okay? All right, using results of example 5 and 6, What is the probability a 3-digit number selected at random is odd? Okay. Oh, I see. I shouldn't have changed the problem. Well, okay, we're going to skip example 7 for now. Basically, what you would do is you would add these, you would put 6 over 5 if I hadn't changed the problem. But I did. So, oh well, I ruined it. Moving on. Permutations. All right, NPR. That equals the number of ways to arrange R things from a group of N things. The order matters and repetition is not allowed. All right, so what we have here is a definition of factorial, which I kind of talked to you about. And again, you guys get a little bit confused when we generalize and have n times n minus 1 times n minus 2, right? Well, you know, specifically 5 factorial, 5 times 4 times 3 times 2 times 1, right? Whatever it is, you start with that number and you multiply until you get down to 1. So 5 factorial is going to be 5 times 4 times 3 times 2 times 1. Okay, and that is going to be 6 times 4 is 24 times 5, which is 24 times 5 is 120. If you want to, okay, you can do some relatively small factorials using the calculator. 5, math, all right, and you go over to PRB, and there you see choice number 4 is the factorial, and you can do it that way as well, okay? So, you know, I mean, it's up to you. You know, you can try and do it this way, all right, and then times 4, or you can write it out. You know, either way, that's fine, all right? You get 144. There will be ones where you will not be able to use your calculator for. Like, for example, if I tried to do, I don't know, let's try like 58 factorial. Let's see if that one will work. As we get to bigger numbers, it kind of overflows the calculator. That one worked. There we go, error overflow. It's too big of a number. So you can't use the calculator to do 100 factorial. All right. Bonus point alert, if you can tell me the number where it first gives you an overflow on your TI-84 or TI-83, I'll give you a bonus point. All right, 7 factorial over 3 factorial. This is the thing here. This is what I wanted to show you. 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1 over 3 factorial, which is 3 times 2 times 1. So what's going to happen here is this 3 times 2 times 1, that's a common factor that can be canceled. So it's just 7 times 6 times 5 times 4. Okay, put that. 7 times 6 times 5 times 4. And you get 840. Now, this one could have been done. You could have just entered it into the calculator as 7 factorial and then divided by 3 factorial, and it would have given you the answer. But as we get to larger numbers, that won't work. Like if I had 100 factorial over 99 factorial, I can't do that on the calculator, but I can.
Alex Mustola, please report to room 121.
I'm going to stop with 4 factorial there, okay? Because 4 times 3 times 2 times 1 is 4 factorial. Because what I can do now is I can cancel that 4 factorial, right? So I've got 7 times 6 times 5 over 3 factorial, which is 3 times 2 times 1, which is going to be 6. Okay, so I have 6 there, and I can cancel those 6's. So it's really just 7 times 5 is all that's left. It's 35 over 1, which is 35. So you can see how canceling there will work. Whoops.
Nicole Harris, please report to the Len office.
Okay, there we go. So permutations. The formula for a permutation is n factorial over n minus r factorial. Or you can use your calculator and use the probability key. So I'll show you one where we do like n factorial over n minus r factorial. You know, we'll just practice a couple of them. 5 factorial over, well, what's 5 minus 3? That's going to be 2 factorial, right? So that's going to be 5 times 4 times 3, okay? 5 times 4 times 3, all right, which gives me 60. Another way of thinking this is like using the counting principle, but you have 3 slots, and you start with 5, and you decrease each time, right? So if I think about that way, if I'm doing 4 factorial, 4p1, it's one slot, and I start with 4, so 4p1 is just 4. 4p4, I'm going to have all 4 slots, 1, 2, 3, 4, right? 4 times 3 times 2 times 1. Okay, and I'll show you that what that's going to be. I think you remember 4 factorial is 24. Let me show you that it's going to be equivalent to doing it with the calculator. 4 PRB, NPR, and then 4. So that's how I do 4p4 with the calculator, and it gives me the 24. Okay? So a lot of different ways to approach these problems. All right, 4p0. If I have 0 slots, I mean, out of 4 things, I can pick 0. There's only one way to do that. And that's what you get. All right, and if you think of that as the m factorial over the m minus r factorial, that's going to give you like 4 factorial over 4 factorial, which you can readily see is 1. All right, so that's what I was just kind of talking about. Nice to know. No, you don't have to memorize this. NPN is going to be 1. NP0 is going to be 1. NP1 is going to be n. All right, so those are just kind of some shortcuts, so you don't have to really even evaluate anything. Next, how many arrangements can be made using the letters from the word computer? So this is like kind of rearranging the letters around, right? And what I can do here is I can take and I can reorder these, right? So I have 1, 2, 3, 4, 5, 6, 7, 8 letters to choose from. So I have 8 choices for the first letter, and that's 7, 6, 5, 4, 3, 2, 1, right? Which is actually going to be equal to, you take the total number, factorial, 8 factorial. Okay, and then you just can kind of evaluate that, 8 math, BRB, factorial. Enter, 40,320. Okay, next. I have 25 seats and 15 students. How many distinct seating charts can I make? So, you know, basically I'm going to take each student, and as they come in, I'll take the first person in the alphabet and pick one of the 25 seats for them, right? So what I'm really doing is, out of 25 seats, I'm going to pick 15 to put kids in. All right, so it's 25P15. All right, 25P15. So 25 math, PRB, NPR 15. All right, ooh, that big number, huh? 4.274 times 10 to the 18th. So lots of seating charts possible. So if I only have 15 kids in the class, I have a lot of different ways. How many letter permutations can be made with the word hermit? That just says letter permutations, doesn't specify like a specific number. So basically, I'm going to take and pick and have all of them, right? So 1, 2, 3, 4, 5, 6. All right. So if I have 6, that's 6 factorial, and I can evaluate 6 factorial. And 6 factorial is equal to 720. 720. Okay. And if the letters repeat, we need to account for that and not count them twice. So like when I have a word like banana, N occurs twice and A occurs 3 times. So if I try and just take all the letters in the word banana and rearrange them, I could get like one that's like B, N, A, N, A, right? Now that's going to be the same as if I then took like that A, this A right here, being that spot, and replacing it. If I switch those two, that's counting that as a distinct permutation. And we don't want to account for that. We want to kind of divide that away. So it's always going to be the total number over the repetition. So when you look at, for example, banana, it's 6 factorial over 2 factorial times 3 factorial. All right, and you can evaluate that. We did one like that earlier. Just practicing mathematics. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 factorial over